Hello, students. David Chatfield here, and I want to tell you about the physical chemistry experiment, the vibrational rotational spectra of HCl. So the purpose of this experiment is to determine structural constants of HCl from its spectrum and also spectral constants. So you'll be able to determine the equilibrium bond length, the vibrational frequency, and constants that describe anharmonic and non-rigid aspects of the molecule. So I'm going to summarize what is in the laboratory manual briefly. Now there is a separate slide video about how to carry out the experiment, so I will not dwell on that. This is a schematic of filling the cell. Here's a brief picture of the spectrometer. So first, a couple of pictures of sample IR spectra. You may be used to pictures like the one on the left from organic chemistry. That is often a solid or liquid state sample. It's very broad. It's not highly resolved. It's useful for sample identification, kind of like a fingerprint. We are going to have in this lab much more highly resolved spectra where we can see the individual peaks. They're highly resolved for a couple reasons. One is their gas phase, not condensed phase. Another is that HCl, it's a diatomic, it's a fairly simple thing. And we have a very highly resolved, very powerful spectrometer. So we'll interpret this to get all the data that I just mentioned. So first, a bit of the theory. This will be covered in lecture, so I won't dwell on it at great length. But the theory is based initially on a molecule of a molecule as rotating and vibrating at the same time. So in the simplest approximation, the vibration can be thought of as a harmonic oscillator. And you have from the model problem harmonic oscillator, the equation for the energy there, where V is a quantum number and this nu is the vibrational frequency. And then we also have for the rotation, the rigid rotor model. You can think of your molecule as, now you think of it as rigid and not expanding or contracting in length. Then you can have a constant moment of inertia, and this is the energy expression. It's really the same expression as you would get for a particle on the surface of a sphere. Okay, it's interesting that they are analogous problems. So we have these two expressions. Now, real molecules are more complicated because they're not rigid. In fact, the previous picture is not entirely consistent, right? If you're rigid, you can't be vibrating. But you could individually have those two approximations to think about vibration in one case, rotation in the other. What happens when you really relax and allow for reality to set in, then the harmonic oscillator approximation has to be extended and the rigid rotor approximation has to be extended. And now we have these various terms here. First, on the left, we have our energy, except we're now expressing it in units of wave number. Essentially, what we have done is to just divide the energy by hc, where h is Planck's constant and c is the speed of light. And that gave us our t. The t is called a term. Okay. Then the next terms, using the word in a different way, on the right-hand side, the first is of course the harmonic oscillator term, and omega e is the vibrational constant. In class, we often use nu tilde, but here it's the omega. The next term is the anharmonicity. This is a correction to the harmonic term. And so the anharmonicity constant is really this double thing, this product of omega e and xe. Sometimes we call xe the anharmonicity constant, but really it's the product there, multiplied by v plus a half squared. The next term is the rotational constant term we saw before for rigid rotor rotation. And the BE is the rotational constant. So it looks like what we saw before, now we divided by HC. The next term is for centrifugal distortion. what you have to have in your head here is as the molecule rotates more quickly, the centrifugal force stretches it. The moment of inertia there essentially increases, and this changes the energy. It actually decreases the energy. So we have a constant that is proportional. Well, the constant here is dE. We make that, let that be positive, but this is a negative sign here. And this is times jj plus 1 squared, so j squared, j plus 1 squared. Finally, there's another term that is the coupling, describes the coupling between rotation and vibration. And so this is proportional to something called a vibrational rotational constant, and that's multiplied by v plus a half jj plus 1. Okay, so you're going to use this expression to model your vibrational rotational spectrum. Okay, so now let's talk about the spectrum itself. Okay, so we have to talk about the transitions that we see. We have to talk about which are the allowed transitions and the selection rules. Selection rules are what tell us what transitions are allowed and what are not. Now, the general principle here is that we start in some initial state and your molecules in that initial state. That initial state is described by quantum numbers v and j. And we'll often use a double prime to describe the initial state. Then there's some higher energy state that we can excite to. Of course, we need some energy, something to excite. So the energy comes from a photon that has some particular frequency. And that will excite us to some upper state described by a new value of v, we'll call that v prime, and a new value of j, we'll call that j prime. Okay. So, so in blue here, we have the different possible initial levels. So in every case, v is equal to 0, but we have a different set of possible values of j. These are all the initial states. Up above, you can call this, if you like, the v equals 0 manifold of different j's. If up above, we have the unexcited state where v equals 1, and again, we have this manifold of different j values. So we are going to see excitation out of the v equals 0 manifold up into the v equals 1 manifold. And these vertical arrows show the various transitions we might see. So let's talk about these. First, let's talk about this line. We're starting in v equals 0, j equals 0, going up to v equals 0, j equals 1. Okay, so that's a delta j equals plus 1 transition. Okay. In the next case, we can go from j equals 1 up to j equals 2. That's also delta j equals plus 1, and so on. Here we go from 2 to 3 and 3 to 4. So all of these together right here are for delta j equals plus 1, and we call this a branch, the R branch. Okay. Now over here in green, notice here we're going from j equals 1, v equals 0, j equals 1, to v equals 1, j equals 0. So this is delta j equals negative 1. Here we have j equals 2 going up to j equals 1. Again, delta j equals negative 1, and so on, 3 to 2, etc. So this delta j equals negative 1 branch we call the P branch right here. And in your spectrum, that's all you're going to see. Okay. For some molecules, delta j equals 0 is allowed. So when delta j equals 0, we talk about a Q branch. However, we don't see the Q branch. It's forbidden for HCl. And why is it forbidden? You'll see later in the class. Okay. So every peak that you see in your spectrum comes from either one of these blue or one of these green or one of these blue or black. I guess they're black transitions. Okay. So Okay, moving along then. So your spectrum. So you'll get the spectrum and you will label it. You can label it down here. It's labeled by the value of J double prime, right? Right. So for the P branch, the smallest value of J in the lower state was 1. In the R branch, 0 was allowed. So these are labeled by J double prime. So P branch and R branch. Now you'll also notice, if you look closely, that every peak is really a double peak. And I'll focus on this one, for example, right here, this peak. You notice there's a tall peak, but there's also a smaller peak. Okay, that's because chlorine has two fairly common isotopes, 35 and 37. So this tall peak, it turns out that 35 is more abundant. So this is H135Cl, and the other one is the H135 Cl37. Okay. Of course, we speak of isotopes when we speak of atoms, but when we speak of molecules that are composed of individual isotopes, we use a different word, isotopomer. Right. So these are the two most common isotopomers of HCl. Okay. So you'll label your spectrum this way, and then you'll analyze it. How do we analyze it? Let's go on to the next slide. So you'll fit your data, and without going through the algebra real fast, and any slowness, you can look at the lab manual and see how to do it. We'll call new tilde here for the R branch. The new tilde is the frequency of the peak in the spectrum, and the peak in the spectrum comes from the difference between the two energies, the upper state and the lower state energy. So that would be T for V prime J prime minus T for V double prime J double prime. That's the lower state. And so when you do some algebra, this is what you get, an expression in terms of omega naught, BE, alpha E, and so forth. Now, omega naught is the difference between this difference that you can see, omega E minus 2 omega E XE. Okay, so there you go. For the P branch, you get an analogous expression. It's just a little simpler. Okay. Now, in this expression, we have not included the centrifugal distortion. We can do that also, but we haven't done it here. Now, you can combine these two expressions as is described by defining M as J double prime plus 1 for the R branch and minus J double prime for the P branch. You get this expression in the quadratic fit, this expression for the cubic fit. You might as well just do a cubic fit. Your resolution is high enough that you can get a value for DE that's meaningful. If you didn't have such high resolution, there'd be a lot of noise and you shouldn't try to get it, but you can get it. Okay, so you will then fit all of the lines in your spectrum using a cubic fit. You can do this in Excel using a trend line with the polynomial trend line in third order, and you'll be able to obtain all of your constants. Now, one additional note, if I go back, actually, you'll notice what you can get out of this fit is omega 0, but you'd like omega E and omega E XE. How do you get them? Well, you can get them by combining the data from the two isotopomers. Okay. So for one isotopomer, we have this definition of omega naught. And when we have no asterisk, we'll be describing the 1H35Cl isotopomer. So for the other isotopomer, we have, of course, this expression where the asterisk just means 37. And you can do a little algebra and get this. Now, where does this come from? Let me tell you where this comes from. Remember that omega E is the square root of the force constant divided by the reduced mass. Now, if that's true, then omega E asterisk will be K divided by the reduced mass of the 37Cl isotopomer. That's that asterisk here. Now, K, the force constant, is going to be the same in both cases, but the reduced mass is different. So you can do a little algebra and write this as and of course, this right here is just omega E. So that's how you get this expression up in right here. And then once you've got that, notice you have two equations and two unknowns. Here's one equation, because this is not an unknown, that's measured from your spectrum. And here's the other equation right here. Okay, so you don't have to think about this part now. This is also measured from the spectrum. So our unknowns are what I'm going to circle. Omega E and omega E XE, right? Up here we have the same unknowns. So we have two equations and two unknowns, and we can determine both omega E and omega E XE, or omega E and XE. Okay. So those are the principles, and you will be getting either measuring in the lab, or if we're not able to do that, you'll get a data file with all of the peaks. So in your lab report, you will from all of the data, you will do your fit, and you'll compute all of the spectroscopic constants. From those, you can even determine the moment of inertia and then the equilibrium bond length. So you'll be doing that. You'll compare all of your data with NIST data. In some years, we've asked people to do Gaussian or Spartan calculations, because you can calculate the frequency and the equilibrium bond lengths with these programs. You've done that before. This year, I'm not asking you to do that, but everything else you are being asked to do. So that's a brief introduction to the experiment, and I wish you good luck.